The dot product is a pretty interesting calculation that we can do with vectors. So the definition of the dot product is if you have two vectors, vector v and vector w, you can find their dot product by doing the following. You multiply a1 times a2, so you multiply the horizontal components together. You multiply b1 times b2, you multiply the vertical components together, and then you add that up, and that's called the dot product. It is important to note that the dot product of two vectors is a scalar, so it's just like a constant. It's not a vector itself, it's just a numerical value. So let's talk about how to do some examples of finding the dot product between two vectors. So if we have vector v is 3, -7, and vector w is -2, 5, their dot product could be found by doing the following. We would say 3 times -2, multiplying the horizontal components together, plus -7 times 5, multiplying the vertical components together. We'd have -6 plus -35, and that would give us -41. Okay? Let's try w dot v. So we would say -2 times 3, horizontal components together, 5 times -7, vertical components together, and we have -6 plus -35 equals -41. Now certainly seeing a single example of this isn't a proof, but it's pretty clear that the dot product is commutative. So in other words, v dot w would be the same as w dot v. Now notice I'm not saying times, I'm saying dot. So we do want to say dot product here. Now we're asked to find v dot v. Alright, so we say vector v's horizontal component times vector v's horizontal component plus vector v's vertical component times vector v's vertical component. That gives us 9 plus 49, which is equal to 58. Okay? And then just a little reminder about what this means. This is indicating find the magnitude. So we will find the magnitude of v, and we see that it's the square root of the horizontal component squared plus the vertical component squared, which is the square root of 9 plus 49, otherwise known as the square root of 58. So what we want to notice in these two, as we look at part C and part D in the example, we could even think of the magnitude of v, of any vector, would be equal to the square root of v dot v. Who knows when that might come in handy. I have a little dot product demo in GeoGebra that I thought it might be neat to take a look at. So I was gonna, if you want to take a look at this and play around with it, I encourage you to do that. I can't emphasize enough the need to really get a hold of these geometrically so they make more sense in the more abstract algebraic sense. So in this applet, you can move the point, the common vertex, I guess you would say, around, common starting point, common initial point around, to make it so that your vectors both show up. So we had vector v was 3, -7. So from here, vector v would go 3 to the right and then 7 down. So I clearly need some more room. So from the initial point, 3 to the right, and then 1, 2, 3, 4, 5, 6, 7. Just barely made it. So I see 3, -7 there. They don't have a w, they have a u, that's okay. Our vector w was -2, 5. So from the initial point, we go 2 to the left and then 5 up. 1, 2, 3, 4, 5. There we go. All right, so we can see the dot product of -41, which is what we got a moment ago, but it is kind of nice to see, well, why are they showing me this? Well, not surprisingly, the dot product can help us figure out the angle between two vectors. And we are interested in that sometimes. I want to kind of play around with this a little bit and just give you an idea of some things. I want you to notice the sign of the dot product and the angle between the two vectors. So we've got a negative dot product here, you see, still negative. Oh, but now it's positive. I just keep moving this around, still positive. Positive dot product, and now it's negative again. So as I'm, just kind of going around here, can you kind of tell what the dot product indicates, what the sign of the dot product indicates? Something else I would like you to consider, I accidentally happened upon it there, this right angle. Notice when the right angle, if there's a right angle between the two vectors, the dot product is 0. We will explore this much more in a later video, but I just thought it would be neat to take a look at that. All right, and then the last thing before we move on to some more topics dealing with the dot product is the properties. So we already kind of saw, we suspected that it was commutative, and it is. We see in item number 2, if you have a scalar multiplying one of the vectors, you can group associatively, so the associative property of multiplication still holds. We see a distributive nature with the dot product. Number 4 is what we recognized with part C and D a moment ago. The 0 vector dotted with any other vector will have a dot product of 0. And when we have, so this one, number 6, looks a lot like number 2, but there is the different grouping there peppered in with some commutative property as well. So take a moment and study the properties of dot product.